Sophia, you ready? We can talk about the generator. First of all, I should say every electric motor is a generator. Every generator is an electric motor. They're the same middle piece. If you want to make it an electric motor, you supply current and you get motion. If you want to make it a generator, you supply motion, you get current. In other words, if you supply electricity, it'll spin. If you spin it, you'll get electricity. So here is a very, very simple electric generator. It says on the end here, rotation. You can imagine that's the hand crank. In fact, this might be one of those rechargeable flashlights where you can crank it and make the light go on. That'd be a pretty good analogy. This is a very, very simple one. We have a coil of wire moving through a magnetic field. It's a single coil because I just want to follow it. And what I really want you to notice, looking at the direction that the coil is moving, I want you to look at the end view. So we're going to scroll down a little bit. I wrote here the generator was invented by Michael Faraday. Here is the end view of the picture on the previous page. Right now, in this top bar, there is a proton. Which way is the top bar moving? Right now, it's moving in this direction. Imagine it spinning. Right now, the bottom bar is moving in that direction. Let's look at a proton sitting in that top bar. Which way is it moving? I'm looking for a word that starts with the letter R. To the right. Everybody point your right thumbs to the right. Which way is the magnetic field pointing? Well, magnetic fields point from north to south, so also to the... Oh, you know what? We have a situation where the proton is moving parallel to the magnetic field. Who remembers when the proton was moving parallel to the magnetic field, what force will it feel? Nothing. You get no induced voltage, and therefore you get no induced current. But now this is going to rotate 90 degrees. Now the top bar has made it to here. Now the bar is moving in that direction. And therefore the protons, Declan, are moving in that direction. Everybody point your right thumbs down the page. Which way is the magnetic field pointing? This is high five hitchhiker Raghav, so straighten out your hand. Down the page. Magnetic field coming out of the page. I got to put my hand like this. Let's try that again. Proton down the page. Magnetic field is pointing to the right, right? From north to south. Which way is my palm pointing? Out of the page. The proton is going to feel a force out of the page on this side and into the page on this side, because this one is moving up. And what you would notice if you hooked up a voltmeter is you would notice that the voltage has just spiked in the positive direction. As it continues to rotate, now the bar that used to be on the top is on the bottom. Now the bar that used to be on the bottom is on the top, but here and here, they're still moving parallel to the magnetic field. What's the force that the proton will feel when we're moving parallel to the magnetic field as a number exactly? Nothing. You're going to see the voltage drop back down to zero. Now, as it continues rotating 270 degrees, the bar on the left used to be on the right. The bar on the right used to be on the left. The bar on the left is moving up, so you're going to get a current coming out of the page. In the bar where you used to have a current coming, so you're going to get a current going into the page. In the bar where you used to have a current coming out of the page, you're going to get a voltage spike, but in the negative direction. You would see this needle go boom, 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 back and forth, back and forth. You would see this needle go back and forth, back and forth, back and forth. And what you would get is a current and a voltage that looked like this. It's a sine wave for those of you who have done pre-calc 12 or calculus. I can't cover it in physics 12 because I can't assume that you've done pre-calc 12, but you look at trig functions in pre-calc 12. AC current is a great application of a trig function. Oh, and then if we go one further back to where we started from, we'd be back to zero. So you get voltage here, voltage here, voltage here, voltage here, voltage here, voltage here. In the middle, the voltage is getting smaller and then getting bigger and then getting smaller and then getting bigger. So what I wrote here, Liam, is that when the coil is horizontal, like in picture B, this is when we get our peak voltage because the two bars are moving perpendicularly to the magnetic field. When the coil is vertical, either in picture A or C or E, we get no voltage. Oh, and in picture D, when we're horizontal again, but the bars have flipped sides, we get a negative voltage. Same magnitude as the positive one, but in the opposite direction. So in the second diagram, I think you turn the page now, yes? Go to page 3. Your maximum voltage can be calculated by BLV, except this equation is tricky to use when there's a coil of wires like we have here, when there's a loop of wire. It's easy to use when it's a single wire. We did that last day, but it's tricky when there's a coil of wires. So this is what Michael Faraday asked. How can we combine the induced voltage of a wire, BLV, and the induced voltage in a loop of wire? Consider the following example. This was his first thought. He said, suppose we have a rectangular loop of wire moving to the right. First of all, this diagram got chopped off a bit. Can you all finish off the rectangle in picture A? The far left side just got chopped off. So draw it in for me, please. You have it? Oh, it just vanished on mine. Oh, none of my other classes mentioned that. Well, thanks, other classes. We have picture A, B, C, D, E, and F. And it's asking, where will there be an induced current? Which two can you say right now there's going to be no induced current because they're not even inside the magnetic field yet? Okay, so cross out A, cross out F. I know that. Now, let's look at these. I'm going to zoom in on picture B, and I'm going to do my old reliable, put a proton in the middle of each wire. I'm going to put a proton there, a token proton there, one there, and one there, because my right-hand rule works for protons. Let's look at the top one. Which way is the rectangle coil of wire moving? Starts with letter R. So which way is that top proton, which is inside the coil, moving? Starts with letter R. So everybody point your right thumbs to the right. Which way is the magnetic field? What do those dots mean? Out of the page. So if I'm facing the front, I would be going like this. What direction will that top bar proton feel a force? Now, the problem is, although it wants to go down the page, it's in that little thin piece of wire. There's no down for it to travel. So even though technically, yes, it is feeling a force, and negatives are technically, yes, getting pushed up, you're not going to separate charges there at all. You're not going to get any kind of a voltage from that one. And the same argument here, you're not going to get any kind of voltage from the bottom one. Where might you get a voltage? Well, here, we have protons moving to the right, so everybody point your right thumb to the right. Magnetic field coming out of the page. You know what? This proton is going to feel a force pushing it that way. That's I for current, and an arrow. What about this back bar? Is this back bar even inside the magnetic field yet? So will these protons feel a force at all? So what you would find in picture B is you would have current moving in this direction. So we're going to circle picture B because that's one place where you would have a current flowing. Clockwise, if you wanted me to give it a direction, because circles are clockwise or counterclockwise. What about picture C? I'm going to do the same trick, Sophia. I'm going to go proton, 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 proton. Same argument, Evan, top and bottom. Yes, they'll feel a force, but there's nowhere for them to go in that thin chunk of wire. And we already answered the front bar question. Which way is the front proton moving? To the right. Which way will it feel a force? It'll feel a force downwards. But now this rear wire is also in the magnetic field. What direction is this rear wire moving? To the right. So which way will it feel a force? Which way will this proton feel a force? Down. What you're going to get are two equal and opposite currents. If you have two equal and opposite currents, what's the net current as a number exactly? Sophia? You're not going to get a current in picture C or picture D, because picture D is the same thing. Ooh, picture E, you know what? The charge to look at is that one there. The top and bottom, we have the same situation. There's nowhere for them to go. The front side this time is already out of the magnetic field, so that proton's not going to feel a force. Here, the rear proton would feel a force pushing it down. Use your right hand rule. In fact, here, you'd have the current going in the opposite direction. You may notice we had the current going clockwise, then we have the current going counterclockwise. This is suggesting this method is going to generate alternating current, not direct current, and yes, it will. This is still a terrible method, but Faraday did this thought experiment, then he did the experiment. He said, why is it that it's only when that rectangle is entering or leaving the magnetic field that I get a current? I don't get a current inside or outside of the magnetic field. How can we explain that? And this is going to bring us to our new concept today, the concept of flux. Ooh, and this is going to be the final brand new unit you learn in this course. So last unit we learned magnetic field is measured in, what are the units for magnetic field? Teslas. Today is your final unit of the course. So to explain this, here's what Faraday said. He said that a voltage, and therefore a current, in a coil was induced when the area of the coil that was exposed to the magnetic field changed. Underline the word changed. I'll go back to this picture. Yeah, you know what? We're generating a current when the amount of area that's exposed to the magnetic field is changing. In picture B, it's going from no exposure to full exposure. And in picture E, it's going from full exposure to no exposure. Those are the only places where the exposure to the magnetic field is changing. That's where we're generating the current. So we need to talk about magnetic flux. What's the symbol for magnetic flux? It's an O with a vertical line and then two horizontal bars on the top and bottom. It looks like a Star Wars TIE fighter on its side. That's the type font symbol. When you handwrite it, most people don't bother putting the horizontal bars on the top and the bottom. I think you can see, Sophia, it's a Greek letter phi on my little chart there with the Greek letters. I think you'll see it's the Greek letter phi or phi, depending on how you want to pronounce it. Michael Faraday, who came up with this concept, was a brilliant experimentalist. Leo, terrible at math. Anything beyond basic equations he couldn't do. And so he didn't define flux mathematically, he defined it in English. Here's what magnetic flux is. It's the number of, I want to write magnetic field, except I don't want to write magnetic field because we have an abbreviation for magnetic field. What letter have we been using for magnetic field? Okay, B, field lines that pass through an area. It's the number of magnetic field lines that pass through an area. More lines, more flux. Less lines, less flux. And when that flux changes, that's when you get current. What are the units for flux? Well, there's all sorts of types of flux. We're specifically talking about magnetic flux, but there's also light flux, energy flux, electric field flux. All flux is measured in lines because it's the number of field lines, but magnetic flux specifically is measured in Webers, symbol capital B, sorry, capital W, lowercase b. Magnetic flux is measured in Webers. How do we calculate flux? Can you find it on your formula sheet, please, so you know what we're talking about? Magnetic flux is the strength of the magnetic field times the area, which I guess, Evan, technically means this is a Tesla meter squared, because magnetic field is Tesla, area is square meters. Yeah. The best analogy I can give you, and I'll need you to look up, is to think of it as the size of a shadow. So here's a circle. The amount of flux in this circle, and sorry for those of you on YouTube, is the size of this shadow. So here's our baseline flux. What's the flux exactly as a number right now? Go obvious. Zero. Okay? No lines are passing through this area. There's no shadow. There's no white area of the shadow. Full flux, zero. This would be partial flux at an angle. Did I say angle, everybody? We're not going to worry about components. If you take this further in an upper level physics or electronics course, you can. I think technically flux is BA. I can't remember whether it's sine or cosine. I'd have to derive it, Kevin. I'm not going to worry about that. I'm going to give you a situation where flux is either full or, everybody, zero. Okay. How can I change the flux? One way would be to make the area bigger. If I replaced this roll of tape with that hula hoop hanging over here and brought it here, you can imagine bigger shadow, more flux. Or I can strengthen the magnetic field. How would I do that? If the projector is the magnet, I could move closer to the magnet. Look at the size of the shadow. Look at the size of the shadow. Increasing, more flux, more lines going through it. So my analogy that I keep going back to when I'm trying to visualize flux is I think of it as the size of that white area inside the shadow. So example 1 says, for each orientation of the spinning loop pictured below, what can be said about the amount of flux? I only drew the front half. You have to imagine the second half of the loop is back there. I just didn't bother drawing it in. Which of these has no flux because the area is parallel to the magnetic field lines? Which of these has no flux? Which of these would have the maximum flux? And this would be medium flux. Again, you have maximum flux getting smaller, getting smaller, getting smaller, getting smaller, zero, and then getting bigger, but in the opposite direction. This again is why you get an alternating current, getting bigger, zero, small, bigger, zero, negative, bigger, zero, negative. That again is why you get that current. It's a sine wave or a cosine wave, depending on how you want to draw it. Example 2 says, describe, turn the page, whether the flux is increasing. I'm going to use a capital letter I for increasing, decreasing. I'm going to use a capital letter D for decreasing, or constant. I'm going to use a letter C for constant. So picture A, we have a coil. Again, Evan, I didn't bother drawing the full coil because I couldn't figure out how to make it look 3D-ish. So here's our coil. It says the magnetic field is increasing. Do you think that will increase the flux or decrease the flux? Yeah, because flux is magnetic field times area. If magnetic field or area gets bigger, flux gets bigger. So this is going to be increasing. What about if the magnetic field decreases? Flux is going to be decreasing. What about if the area inside the field decreases? What's happening to the flux here? What's happening to the number of lines of magnetic field that are passing through this area? I hear the increasing. I didn't hear the first syllable. Yeah, this is going to be decreasing. And Declan, a way to think about that is if this is my area, there, smaller white area, that's what that picture is trying to indicate. Again, sorry for those of you at YouTube. Good luck. This is the picture that we looked at last day. We said this was a terrible way to generate current, but it will generate current. What's happening here? So this is an increasing flux. This is where I realized Faraday was so much smarter than me. He looked at this and he said, there is an area that's increasing. It's the area behind the rod. This area here, as this rod moves to the right, the area behind it's getting bigger. We are changing the flux. I never would have thought of that in a million years. And that's where I take my hat off to Mr. Faraday and say, probably the best experimentalist of all time. He's really good at visualizing and coming up with experiments. What's the changing flux? What's happening to the flux here? Increasing, decreasing, or staying the same? This is going to be a constant flux staying the same. What about here, where we're moving the north pole of the magnet towards the coil? Well, if you move the magnet closer, does the magnetic field get stronger, weaker, or stay the same? Get stronger, so what's going to happen to the flux? Yep. Ooh, spin the coil. So I guess we're starting off. I've got to rotate my coil 90 degrees because I can't do it this way. Initially, all the magnetic field lines are going through it, pointing upwards. If I spin the coil 90 degrees, what happened to the flux? So did the flux increase, decrease, or stay the same? This is a decreasing flux. This is the best way to generate current. The best way to generate current is to spin a coil. We'll talk about that in a little bit. H, is the flux increasing, decreasing, or staying the same? How do you calculate flux? What was the equation, Kevin? What's happening to the area here? So what's happening to the flux here? Yep. Decreasing. I is a bit tricky. First of all, it's saying that the current in the wire is increasing. So as this increases, if I use my right-hand rule for current carrying wire, I can tell you that the magnetic field here is coming out of the page. As we increase the current in this wire, what do you think happens to the strength of the magnetic field? Increases. What happens to the flux? So flux is the number of magnetic field lines passing through a given area. And so here's what Faraday said. Previously, we said that you can induce a voltage when we change the field, the orientation, or the area in the field. We can now summarize that even more briefly. If there is a changing flux, you'll have a current. If flux is constant, no current, no voltage. Faraday found that the amount of voltage you get, it varies directly with the flux change. More flux change, more volts. In fact, it's going to be on the top of our fraction. It varies inversely with time. As time got smaller, voltage got bigger. That means T is going to be in the bottom of our fraction. And it varies directly with the number of loops of wire. The number of loops of wire, we're going to use a capital N for that, the same way we did in the solenoid. You want twice the flux, use 2 wires. You want 13 times the 13 times the voltage, use 13 wires. Oh, you want 28 times the voltage, you better use 28 wires, which means, Declan, we can really customize the voltage that we want our generator to output. Here is Faraday's law. We're again, even though the answer is the voltage, we're going to use the induced voltage, the EMF. It's equal to N change in flux over the change in time, except it's negative, the whole thing. Why negative? Next lesson, I'll explain it. But can you find that on your formula sheet and see if that's what I gave you? Yes? Doesn't matter, it's on top. Right? Okay. Any number that's right, any number that's outside of the fraction is technically over 1, so it's on top of the fraction by default. What's N? Number of loops or coils of wire. What's flux? BA in Webers. What's delta T since physics 11? Time. And in fact, you're going to notice I stopped writing the delta because time is always changing. Okay. Ooh. What's change in flux? What's change in anything? So change in flux is going to be BA final minus BA initial. Final minus initial. I wrote y negative, tune in next lesson, but here we go, example 3. I kind of like example 3, except this is a terrible way to generate electricity, but I like the concept. I like the concept, so I'll say, I guess, I like example 3, I like example 3, I like example 3. A circular, a what loop of wire? Okay, we need the area of a circle. Anybody know the area of a circle? It's on your formula sheet if you forget, but I'll write down right here, A equals pi r squared. Of radius 2.5 centimeters, I'll have to convert that to meters, is in a magnetic field of 0.4 Teslas, fairly strong magnetic field. If the loop is removed from the field in a time of 0.050 seconds, what's the average induced EMF, the voltage? And it gives me a picture. Okay. Is there a coil of wires or a loop of wires? They're asking me about an induced EMF. I'm going to use Faraday's law. E equals negative N, change in flux over change in time. Sophia, can you read me the very first word of this question? It's a single letter. Say it again. What's N? How many coils of wire are there? Can you read to me the first word of this question? It's a single word, starts with, it's a single letter. How many coils of wire are there? One, okay? Don't miss out on that. Circular loop. So N is going to be 1. I'll make a little note here if you want to. N equals 1. Until you get very good, I would not try doing this all in one step. What's delta T in this question, Sophia? What's the change in time? Those two, N and delta T, are plug and chuggish. What's not is the change in flux. I'm going to draw a little line, and I'm going to find the change in flux over here, which is going to be final minus initial. Conveniently, I can tell you the final flux by looking at the picture. What's the final flux exactly as a number? So I'm going to cross that out. I'm going to get a change in flux equals, the negative drops down. How do I find flux, BA? The change in flux is going to be negative B, what's A? Pi r squared. I've scrolled down, negative, what's B? Fairly big magnetic field, times pi, times, was it 2.5 centimeters? I'll have to convert that, divide by 100.025. Don't forget the squared. What do you get for the changing flux? Negative 0.4 times pi times 0.025. Don't forget the squared. I get a pretty small number. I get negative 7.854 times 10 to the negative 4. I'm going to write negative 7.85, but I'm going to store this on my calculator. So I get negative 7.85 times 10 to the negative 4. Units, what were our new units for flux? Yep, Webers. And now I'm going to walk this right up to here. It says the induced EMF equals negative. What was N in this question? Normally in your homework, you can skip writing the 1. I'll put the 1 down so that when I'm studying, I know, oh yeah, I noticed that. And I'm literally going to write answer button divided by, what was time? How many volts are we going to generate with this system? 0.015 what? 7 rounded off. 0.0157 volts. I look at that and my first thought is, meh. But it's a start. Physically removing the coil from the magnetic field, terrible way to go. Yes? Not getting that? Okay, give me a second. Ah, wrong button. Example 4, a square. Ooh, what's the area of a square? Area of a square is the length squared. Mr. Dueck, is that why they call to the power of 2 squared? Yeah, and it's going to blow your mind. Do you know why we call to the power of 3 cubed? Because the volume of a cube is the length of one side cubed to the 3rd power. Wow. A square coil of wire, 5 centimeters, I'll convert that, has 100 turns. Oh, N is 100. It lies perpendicular to a magnetic field of strength 0.02. If it's rotated through 90 degrees in a time of that, what's the average induced EMF? So initially, if this is my flux, this is my coil, I know this is a circle, but it's perpendicular. Here's the magnetic field. This is the light beams. It's perpendicular. It's going to rotate 90 degrees. What's the final flux going to be? I'll remember that. It wants the induced EMF. That's going to be negative N change in flux over change in time, but I'm getting lazy and I didn't even bother writing the delta T. I just put the T. Evan, what's N? How many turns of wire or coils? I'll remember that. I'm not going to write it down. I've got that in my brain. What I'm going to spend most of my time working on is the change in flux, which is going to be final minus initial, although we already realized the final is going to be 0. So we're going to get a change in flux of negative BA, which is going to be negative B 0.02 A 0.05 squared, L squared. This one should work out nice. You should get a nice number here. Give it to me in scientific notation. No. -1? I think you forgot the squared on the 5. I think you're going to get a -5 times 10 to the -4, I think. And that's going to be, what are our new units for flux? Webers. And now I usually just draw an arrow to show I'm walking it over to here. So the induced voltage, if this is one of those hand crank flashlights, is negative 100 answer button divided by 0.002. Mr. Dueck, where'd the 0.002 come from? It's 2 times 10 to the -3, but that's less typing or writing. I think you're going to get an even answer, like a nice answer here. In fact, I'm pretty sure you're going to get an answer that has a 2 and a 5, because I'm getting a 2.5, not 20, 2.5? Double check me, anybody? Is it 2.5? Yes? That's not bad. That's closer to like a standard little household battery, 1.5 volts. This is almost 2 batteries put in series. You want more? Add more coils. Or turn the crank faster. This is a little better, but the best way, if you want to generate a bigger voltage, is not just spin your coil, it's to actually change the magnetic field. So I wrote here, we can also change the flux by changing the magnetic field. But because magnetic field is a vector, if there's a change in direction, Declan, we need to let one way be positive and one way be Negative. So example 5, I like example 5, I like example 5, I like I shouldn't have listened to Jacob. It's negative 5 times 10 to negative 5. Okay. I won't listen to Jacob again. Ever. Man, this is the one that's going on YouTube. I should have typed it in myself, and I didn't. Should never have trusted you folks. Okay. Sophia, coming back to here, it says this, a circular coil. Okay. Area is going to be pi r squared. If you forget, that is on the back page of your formula sheet. With 100 turns, oh, n is 100, is exposed to a changing magnetic field. Here's what I want you to notice. What direction is the magnetic field pointing in the original picture, in the first picture, in the initial? Kevin? Oh, I thought you said it. Sorry, someone said it there. Up. What direction is it pointing in picture number 2? Is there a change in direction? I'm going to need to let one way be positive and one way be, okay? I'm going to let final be, I'm going to let this one here, since it's down, be negative. I'm going to let this one here be positive. You could do it the other way around. No biggie. It's all relative. What's this asking me to find? Average induced voltage. You know what? That's asking me to find the EMF. So I'm going to use Faraday's law. The EMF is negative N, change in flux over the change in time. And I know N is 100, and I know the change in time is 0.12. I've got to calculate the change in flux. I'm going to do that over here. Change in flux. What's change in anything? And then what's the equation for flux? So it's going to be BA final minus BA initial. What's changing in this case is the magnetic field, not the area. So let's keep going. The change in flux is going to be, what's my final magnetic field as a number? Be careful. Negative 5.4. Area is going to be pi times r squared. What was, oh, they told me in the picture here, radius is 10 centimeters, so 0.1 squared. Minus, what's the initial magnetic field? Two very large magnetic fields times pi times 0.1 squared. How big is the changing flux? Negative 5.4 times pi times 0.1 squared minus 7.8 times pi times 0.1 squared. I get negative 0.41469, blah, blah. I'm going to write negative 0.4147, but I'm going to store this on my calculator. And our new units du jour, Webers. Is that right, by the way? Everybody get the same thing? Okay. Walk it over to here. I'm going to get the EMF is negative. N was 100, I believe. The changing flux, that's going to be my answer button, divided by, and I believe the time was 0.12. Let's see. I think this one is more substantial. I'm doing some quick math in my head. I think you could get an answer in the hundreds. I don't trust ACHI. Oh, 346 units, volts. Hey, that's better. I got 120 from the power outlets here. This is very nearly 3 complete power outlets. It's almost 45. It's almost 360 volts. Not quite. Good yawn? Okay. On the next page, I should mention, so our equation, E equals negative n, change in flux over time. As far as I'm concerned, Leo, this thing contains 4 variables. I can give you any 3, you can find the 4th. I might give you the voltage, the change in flux, the time. How many coils of wire are needed? Or get the T by itself. Or if I really want to be snotty, there's actually more than 4 variables in here, because you also have the final area, and initial area, or final magnetic field, initial magnetic field. I could have you get one of those by itself. I would consider that a fairly advanced question. Like, that would be an example of a nasty multiple choice I might put on. You're not going to get that on a quiz as an easy question that I expect all of my students to do. Last one, example 6 says rank the 4 loops below in order of increasing induced voltage. Okay, so we want to start with the smallest. Which of those would have no induced voltage? A, B, C, or D? So, what causes induced voltage? N, which isn't changing, T, which isn't changing. Oh, if there's a changing flux, remember, flux is the number of magnetic field lines pointing through an object. Which of these 4 diagrams has the same number of magnetic field lines pointing through it before and after? B, which of these has a flux of exactly 0? Same answer. Which of these will generate the smallest possible voltage, which is to say, nothing? Next one, A, D, or C. I think D, because I think what they're saying is squeezed a bit. What they're saying is we reduced the area a tiny bit, which would induce a flux, but nothing major. So I think I'm going to go D. And now I'm going to compare A and C. Which of those would have the smallest flux, A or C? Because it only goes halfway out of the magnetic field. Some magnetic field lines still point in it, haven't changed. And then A is the biggest because it goes all the way out of the magnetic field. I don't know why I wrote D again. I said A, didn't I? A. I tried to cover it up by using the D and pretending it was like intentional. Not really. So if you want me to be technical, if it's a moving wire, use BLV from yesterday. If it's a spinning coil, I would use, except the only problem is I forgot to put in the negative. I'm going to have to fix that. I would use EMF equals negative N, change in flux over change in time. Why is it negative, Mr. Dueck? We'll talk about that next lesson. Next lesson, I will also show you as close to Harry Potter wizardry as you'll ever see. And I will, next lesson or the lesson after, show you the actual real-life physics of what would be a hoverboard, not the Hollywood garbage physics of, oh, it's a hoverboard. It's got wheels. They're touching the ground. No, that was dumb when that craze came out a few years ago. They were calling those hoverboards. No, they're not. Hoverboard should hover. And I will show you the physics of how you could build one. By the way, spoiler alert, you need a fat ton of energy, of electricity. But it's doable. What's your homework? Number 1. Number 2. Number 3. Number 4. You can skip 5, although 5 is really cool. I'm going to cross it out, but I'm going to talk about it. If any of you get into search and rescue from helicopters, it turns out a helicopter's rotor is like a coil spinning through Earth's magnetic field. And they actually generate on the helicopter a pretty big voltage. They separate charges such that when you're lowering a metal cable down to rescue someone, that person can get a hundreds of volts, fairly significant shock, enough to injure them, especially if their heart is already in bad shape from the injury. You have to take that into account. You have to ground it. So what they will try and do either is send a rescuer down first, and then that person has a grounding pole that they will put into the ground, hold an insulated pole with some metal on the end, and try and discharge anything through there. Or they'll try and lower a metal stretcher down, have it hit the ground, not right next to the person, discharge it through the metal stretcher. But you do have to take into account, if any of you go into search and rescue and you happen to remember this speech, come and talk to me and go into the details. I'd love to find out more. Yes? Confirm this. I'm pretty sure this is my understanding. Based on this, the physics makes sense. I've never been injured in such a way that I had to experience it, and it's not like I felt comfortable tagging along on one of them or something. I'd love to know. Number 6, circle but cross out A and B. A wants, you can do the BLV questions with Faraday's law. It works, but it's just dumb. I wouldn't do it that way. You can use negative change in flux over change in time. No, I would use BLV. Okay. Um, you can skip 7 for now. Really, a lot of you still have to work on lesson 1. Lesson 1, the first question from the homework, is a really neat one. Evan and I were doing it yesterday, and I was reminded it explains why, because cars are made of metal and they're traveling through Earth's magnetic field, if you're going in the right direction, one side of your car will become positively charged, one side of your car will become negatively charged. It explains why on a dry, wintry day, when you get out of your car, you can often get a massive shock because you've actually built up a fairly substantial voltage. So that was, where was it? Number 1. The only problem with number 1 is it's worded a bit tricky. I'm going to change the wording to make it a bit easier. But otherwise, it's a cool question. Anyways, homework from last day, homework today. You have the remainder of class. Let me press pause on the video.